Hello dear students, welcome to the lecture series on Verilog HDL. This is lecture number 5 of module number 1. Now these were the topics that were covered in the previous lecture, that is difference between modules and how to create the instances of those modules, and we have seen few examples of Verilog program wherein we try to generate different instances of particular Verilog module and we try to verify the correctness of the program. Now, today in this lecture, we're going to write a Verilog program. In the sense, we'll see how using the concepts of comments, number specification, and white spaces, how one can effectively write a Verilog program. So that will be the contents that are going to be covered in today's lecture. Now, basically, Verilog HDL is a case-sensitive language, and all keywords are in lowercase. Verilog contains a stream of tokens, and tokens can be like comments, delimiters, numbers, strings, identifiers, and keywords. We're going to see one by one what exactly each one of those mean. Now, in today's lecture, like I was telling, we are going to highlight mainly on the comments and the numbers. In the upcoming classes, we're going to see the other stuffs as well. Fine. Now, comments are very important for any particular language because whenever we try to code in any particular language, comments play an because comments are those things which help us to understand what has been written in the entire program, and there are different ways to write the comments. So basically, comments are inserted in the code to increase the readability and proper documentation. Now, even in the industry standard, program without a comment is considered as a null and void, because though comments doesn't do any particular job with respect to the logic, but they surely help us in better understanding and readability of any particular programming language. And Verilog also have certain kind of comments, the way how we can write the comments. So basically, the comments can be written in multiple ways. There are two ways of writing the comment. That is one line comment or a single line comment and multiple line comment. So one line comment is nothing but whenever I want to comment out a particular line. So basically, comment, like I was telling, are those things which will not be executed or which will not be synthesized, but it will enhance the readability. So whenever I write anything with the backslash like this and whatever the things I write over here, this particular aspect won't be executed, but that is visible to the programmer, and you can easily make out what has been written in parallel to this particular Verilog code. So that will definitely enhance the readability and proper documentation. Now, like I was telling, there are two ways to write the comment. One is a single line comment, like for example, this particular line, and I want to comment this line, and I don't want to delete this. So rather, what I can do, I can just put a double backslash slash something like this. Even if I want to name it, like for example, this performs the AND operation between B and C. If I want to name it here, then I can use the comments and I can name it. This particular option is available for the single line option and single line comment. Now there is something called as multiple line comment, wherein you want to comment the entire paragraph or an entire set of lines which you don't want to execute and which is only meant for documentation. In that case, I'll be using backslash star at the beginning of the line, and at the end of the line I'll be using star backslash. So this entire portion will be commented out, and this won't be synthesized, or this won't be, in a simple words, this won't be executed. But this surely help us to read that particular task, what is happening beside that comment. It will enhance the readability. Now, there are certain important aspects that one has to remember. Of course, these are the ways to write the comment, but as a programmer, I should be aware of how I should not write the comments. So this is one illegal commenting which I have shown over here. See, I cannot be putting multiple line comments option within another multiple line option. See, like I have a star, backslash star, and again star backslash. Now this is a legal commenting, and inside this I cannot be putting one more backslash star and star backslash. So this entire stuff become an illegal commenting. I cannot be doing this. But whereas I can be doing surely this way. Within a multi-line commenting, I can put a single line comment. So this is acceptable. So this way I can write, but not definitely this way. So this is all about your commenting option. That is the first kind of tokens. Now one of the major aspect in Verilog is how do I write different numbers, or how do I specify different number systems that are available in my entire Verilog language. So like I was telling, we have to represent different numbers, and numbers play an important aspect in any programming language, and so is the case with Verilog language as well. Now there are two types of numberings that are available in the entire Verilog language, that is your sized number and unsized numbers. Now each number's representation has got certain formats, and we'll see the in detailed version of the formatting of number system. And for that I'll just like to move to one more. Yeah. Now here you can see, so whenever I want to represent any particular number system, so I have to represent it in a particular format. So any particular number has got certain prefix things that are being attached to any particular value. That is your size. I represent it by a separator, which is I name it as tick. There's a single quote bar stick, a kind of a tick, and then I represent whether it is assigned or unsigned, and I represent the radix in the sense in which number system it is present, and then I write a value. I'll show an example how to utilize all these things and then write a value. But of course, all the things that are being written behind the value, except this tick, they are all an optional part. Look here, all the things that are represented in the triangular braces, they are all optional part, meaning I can even represent any value without the help of these things, and under that scenario it will consider a default number system. And what is that default number system it is going to consider? We'll see that. So basically, size, it indicates the number of binary bits that particular value is comprised of, and not the hex or decimal digits. It is, when I say size, it is in terms of binary bits. Like for example, if I mention 8, then I cannot say the size as 1. The size will be by converting 8 into its binary representation, whatever the value it comes, that will be the size. So if I represent 8 over here, if I write 8 over here, what will be the minimum size? That will be 8 is represented as 1 0 0 0. So the size is 4. But now in the Verilog language, the default size of any particular value is 32. If you don't mention anything, if I just mention 8 here, it means 8 radix in which particular number system that 8 belongs to. I can mention that. Like for example, if I consider, I write B and then I write 1 0 0, and then I represent whether it is assigned or unsigned by using the alphabet S. Then if I don't mention the size, then though you have given the number as 1000, and it is quite visible also, the size is 4 bits, but since you are not mentioned anything over here, the size, default size that will be stored in the registers of your Verilog synthesis block will be 32 bits until and unless you mention it. So otherwise, how do I mention it? I mention something like this: 4 tick signed B 1000. Even if I don't mention this particular signed representation by S, it is considered as a signed number. So we'll see with few examples. Now this is how the different values and the prefix values are represented. For a binary number system, I use a prefix of B, octal O, decimal D, and remember all these prefixes are having one more component, that is single code. We call it as a tick. Tick B, tick O, tick D, and tick H. And what could be the possible legal numbers I can write? I can mention any possible numbers. Of course, binary has got two numbers, 0 and 1, but there I can also write X. X indicates it's an unknown or a don't care condition. Now I can use either small letter X or capital letter X, both means one and the same. And I can use Z also. Z means it indicates a high impedance of that particular bit. And I can use the underscore. This underscore is basically to increase the readability, nothing more than that. It's one more, it is called as white space. Like for example, you can see here this number If I the moment I use underscore in between, I can easily read it like 2AE5. I can read it. And then I can use the question mark also. Question mark also indicates a kind of don't care. I can use either X or a question mark. So these are the different legal characters I can use for different number systems or different numbering format. Like I was telling, if a prefix is preceded by number, then number defines the bit width. Like for example, we'll see with the help of an example. Let me go here. Yeah. Now, as of for time being, don't consider or don't worry much about what is reg. I'll just tell you what a reg indicates. It's a register, a kind of memory block, a vector. So it has got a register has got an 8-bit value, and it can store up to an 8-bit starting from 0 to 7. So that's what I have written over here. We can store 8-bit binary numbers in its memory. But now again, for timing, don't worry about this dollar display. Dollar display is basically used to display the values on your screen. When we do the simulations, we'll try to get in depth of this particular display option. Now when I display the value V over here, and then how is that I'm going to get? V is written as 4 times 0, 1 0 1 1. Why 4 zeros has been appended behind this one? That's because you have mentioned it is an 8-bit, but what are the values you are given? It is only 4-bit. And what is the size of the register? It can store up to 8-bit, and then the remaining terms will be filled with zeros. MSBs will be filled with zeros. Now if I consider the same case with respect to the other thing, like for example, I have 0 to 7 bit, and then I have written here 3 is equal to W is equal to 3 tick B 1 0 1 1, and then I display it. Now what will happen here? You can see over here bit 3 truncated and then filled. So there is a reason why this particular case is happening. I'll try to take up this aspect when I take a simulation over here. This is a very particular case with respect to the Verilog language. Why after appending this first bit is truncated. That's because look here, you have written the value as 1011, and you mention, because these are the 4 bits, and you mention it as a only 3 bits. So when you write 3 bits, so like I was telling, since the number of bits you have represented as only having a 3 bits, but the numbers the number of bits you have represent here are 4. So the last bit will be truncated, and then it will be appended with the rest all bits with 0 bit, because it can be stored. It is going to be stored in a 8-bit register. So this is how the truncation happens. Moving ahead, let's see how do I represent with respect to signed and unsigned. So basically the signed numbers are not necessarily sign extended, because sign bit is the MSB of the size and not the MSB of the value. I'll tell you what exactly this line mean. Like for example, see, this is how I represent 8 tick HA. H indicates it is an hex value, and it's an unsigned value since I have not mentioned anything. And 8 tick SHA means S indicates it's a signed value. Now for unsigned value, we need not to worry about what is the sign over here. I just convert 8 into its binary representation 1010, and since you are representing it in the form of 8 bits, append the values to 0. But when it comes to signed number, so signed number like the MSB represent the sign. Now that sign value should be considered only when you append the values and make it as an 8-bit, because here you have mentioned 8-bit. So the number is A is 1010. Now don't consider the MSB of A, the last the MSB over here as 1, and say it as a negative number, because it is having a value of 1 for the MSB. Because you remember, negative numbers are represented with MSB value of 1, and positive numbers are represented for MSB of 0. Now don't consider this as a negative number because I need to yet make it as a 8 bit. So how do I make it as 8 bit? You append the rest all bits with a 0. You append it. Now this is a full-fledged 8 tick signed hex value of 8. Now look into the value of the MSB. It is a 0, which means this is a positive number. So this is what is the intention of talking with respect to signed and unsigned. Now we'll have one more example. Let's not get into all these things. Now look here. If the MSB of any particular signed number is 0, then sign extension will occur with respect to that particular value. And if the MSB of any particular value, our number is 1 and that number is a signed number, then again sign extension will occur. For example, okay, let's take a P1 value. It is going to be stored in a register of 12 bit. Now what is the value you're going to store? You are representing the value as 4 tick signed hex value of A. So first I'll write the value of A. A is 1010, hence a 4 bit, and it is going to be stored in what particular value of register, a 12 bit value. Now here, and since it is represented as sign, so you extend the particular number with the last bit and make it as a 12 bit number. And then you see over here, what is the last digit? It's a 1 and it indicates a negative value of this particular A. So that's how the extension. Here also I did the same thing. Yeah, 8 over here. So 8 is represented by 0001010. Now anyhow you are going to, like for example, instead of this 8, if I have written here 10 and the number is only 8 bits over here, then I would extend whatever the MSB that is present over here with respect to that, and then again I will consider the last bit as a sign. So anyhow the last bit now here comes to be 0. It is a positive number. The same thing is happening over here in this particular case. Now let's take one more example. I want to store number A, which is of 5 bit, in a register which is of 12 bit. Now very interesting case over here. Now I am representing the number as a 5 bit number. So basically what is the value of A? The A value is 1010. Now I cannot claim that 1010 is the number A and I'll extend with the last bit with which is as represented as 1 with a value of 1, and I'll append the previous values with a value of 1. Look here, what is the actual size of your data? That is A. It's a 5 bit. So 5 bit indicates you have to represent A with first 5 bits. So 5 bits will be 0, 1, 2, 3, 4 here, or 1, 2, 3, 4, 5. So up to here is your A. Now you look here, sorry. Now look over here, what is the value of the last bit of the MSB of this A? It is 0. Now you append the values to 0. And finally, lastly, after our appending, you can just check over here. This is your sign bit. So since it indicates 0, so it's a positive number. Otherwise, what would have been the number 1010? If I consider only the last bit, the MSB, which is 1, I would have said this number as a negative because it is having a value of 1. But no, it is not that case, because since I am representing A as a 5 bit number, so first you represent the entire A in a 5 bit pattern and then extend with that number which is present at the MSB. So this is how your extension occurs with respect to your number systems. And now literal numbers can also carry a sign. For example, I can represent the decimal number with a negative sign itself, because unlike in your binary numbers, which is represented with the help of signed and unsigned, that is 2's complement and 1's complement, I represent the negative numbers with the help of the 2's complement method, or I extend the last digit and make sure that sign is represented. But when it comes to the decimal number representation, I can directly use a mathematical negative sign over here, and I can say that 15 is a decimal signed number and it's a negative number. So this is how I can represent with respect to decimal number. Now, there are some more examples that I would like to quote with respect to some numbers. Let's take one by one. Like for example, I want to store 8-bit number A6, that is hex number, which is a signed number in a register of value 12-bit. Clearly A6, how can I write? A is 1010, 6 is 0110. Now this is a 8-bit number and I got that 8-bit number. Now this 8-bit number has to be stored in a register having a 12-bit value. Now what are the numbers that I need to, what are the bits that I need to append behind? You have to append the one which you find at the MSB of your actual number A6. So A6, this particular number has got a value of 1. You append all the previous bits with the value of 1 and make it up to 12-bit, and then this goes and stored in the register. On a similar note, let's interchange this number. Like for example, I want to store 6A in a register of 12-bit. Now represent the 6A in 8-bit form. So that will be 0110 1010. So this is my actual number, 8-bit number. Now again, this number has to be stored in a 12-bit numbering format. So the last bit or the MSB of this actual number is having a value of 0. You append the remaining bits with a 0, making it a this particular number. Look at the difference. So appending the previous bits with what exactly you have the value for that MSB matters, and that too once you get this 8-bit formation, because you have represented here as a 8-bit, right? Now if for example, if I have represented it as a 6-bit, then possibly these two would be truncated, and again the rest of the things will be appended with 1, because now after truncation this will be the last number. Here also, if I would have taken here it as a 6 tick, then this entire 6A is represented as a 6-bit, and once I write 6A, it is an 8-bit, and if I want to represent the same thing in a 6-bit format, these will be discarded. And what is the MSB now after discarding? 1. Now that will be extended behind. So this is the theory behind the truncation and the extension. So we'll take one more example wherein I don't mention the value of the number of bits that particular number is having. For example, I just mentioned tick signed value A6, and that has to be stored in a register of 12-bit. Now since I haven't mentioned the size of the number, by default size will be 4-bit and 4-bit. So 8-bit representation I write it over here. Since I haven't mentioned anything, so all the values will be appended 000, and remember what will be the size of this entire number? It will be 32 bits long, because by default the value of any particular number in Verilog will be 32 bits long. But I cannot be storing 32 bits long number in a 12-bit register. So what I'll do, I'll truncate all the remaining values, and I'll see to that only the required amount of values will be appended after this particular representation A6. Only this will be stored in the register. If I do the other way, signed 6A number, here it was A6. So first I'll write it here 6A, and then it will be appended with all the zeros, because I haven't mentioned anything over here. And why I am appending with 0? Because the last bit is 0 over here, and the 32-bit number will be formed. But ultimately what will be the value that is going to be stored over here? The 12, these particular 12 bits will be stored. So hence I will be having a value of this number to be stored in the register D. So that's how your entire exercise occurs with respect to your number system. So this is what I just wanted to talk with respect to the number system. Now moving ahead, like I was telling, there is something called as white spaces. So white spaces are something called as which helps us to increase the readability, and sometimes we used to write certain blank spaces, tabs, new lines, and all those come under the white spaces, and they are represented with different formats. Blank spaces are represented by \b, tabs with /t, new lines with /n. If you write any line, if I write /n, so whatever the line you are writing next, it will be taken the next line. So that's the meaning of that. And if I write t and something over here, one tab space will be given. So this basically all these will help us to increase the readability and better view of the program. And like I was telling earlier also, question mark and underscores, they are basically used to again increase the readability. The underscores are basically used to increase the readability, and question mark is used to as an alternate for Z sometimes, and alternate for don't care conditions. So basically this question mark will be used. So we'll try to cover this question mark aspect in the programming simulation, wherein we'll see how this question mark x z values are used, and these are all they help us to increase the readability. So for example, like here 4 tick b 10 question mark 2 question mark, because I don't know what is over here, so I can write it as 0 or 1, and I can even represent the same thing with the high impedance value. I can represent these two bits which are represented in the question mark in the form of a z value as well. So this is all about your comments, white space and number system that I wanted to cover up in this lecture. So we'll try to wind up in today's lecture with respect to these aspects, and we'll try to cover the remaining aspect in the next lecture. So before heading to the summary, so these are the two questions that one can expect from the examination point of view. That is, explain the different ways of representing numbers in Verilog HDL, and write a short note on white space, comments and numbers in Verilog. So to summarize, in this lecture we try to understand how to write a Verilog program using comments, number specification, white spaces, and how they assist us in increasing the readability, and how various forms of number systems that are available in the Verilog language. And since all these concepts require recalling and understanding of certain facts, this entire lecture comes under level 2 of Bloom's taxonomy, thereby mapping to course outcome number 1. Now, for additional learning and video links, you can refer the links already given in the PDFs, and here is also certain links I have mentioned over here, wonderful references that are over here. And to get into the application point of view, so basically this entire lecture falls in the application of representation of number system and enhancing the readability of any program. So number systems through Verilog programming was one of the application with respect to this particular lecture. So I would like to thank for patience listening. So I'll be winding up this lecture. We'll be meeting in the next lecture.